As you can see on your screen, we're going to be working on sections 4.2 and 4.3 together at the same time because the concepts are very similar. The title here is Direct Proofs and Counterexample. We're going to be working with rational numbers and divisibility. So most of our proofs will involve working with rational numbers and divisibility. What is a rational number? We say that R, which is a real number, is rational if and only if R can be written as A over B, where A and B are both integers and B is not equal to 0. So in other terms, for something to be called rational, you should be able to write it as a fraction where the numerator and the denominator are both integers and the denominator is not equal to 0. Vice versa, if something is a fraction of two integers where the denominator is not equal to 0, then the number that you're working with is going to be automatically called rational. Something that is not rational is going to be called irrational. A real number that is not rational is going to be called irrational. Let's begin with the first theorem, 4.2.1 in your book. It says every integer is a rational number. Is this true? Do you believe it or not? Do you believe that every integer is a rational number? So like for example, do you believe that 5 is a rational number? You should convince yourself because 5 is 5 over 1. Similarly, if I had negative 3 for example, negative 3 is the same thing as negative 3 over 1. As you can see in both examples, the numerator and the denominator are always integers, and the denominator is not equal to 0. So that makes it exactly the definition of a rational number. So that means that those numbers are rational. So to do the proof, we're going to start with a number that is an integer, just like I started with 5 and negative 3. And I want to show that that number is rational. Now I know that the number m is the same thing as m over 1 because divided by 1 does not affect the value of m. It just keeps it as m. And keep in mind that the numerator and the denominator are both integers. So that's important. I have to know that the numerator and the denominator are not any other random numbers. They have to be integers. On top of that, I need to know that the denominator is not equal to 0, which it is in this case. It's not equal to 0. It is true that 1 is not equal to 0. So therefore, m, which is the ratio of two integers, and the denominator is not 0, means that m is now a rational number. And that's what we wanted to show in this theorem. The next theorem says the sum of any two rational numbers is rational. Well, how do we show this? We're going to start with two rational numbers, m and n. And we want to show that the sum of them is rational. Now, because they are both rational numbers, then by definition of rationals, we can find the following. A, B, C, D, which are integers, with b and d not equal to 0, such that m is equal to a over b and n is equal to c over d. So by definition of rational, since m is rational, m can be written as a fraction. And similarly, n can be written as a fraction. I decided to pick different letters for m and n. I decided to go with AB for m, CD for n, because if I picked them the same, that would imply that m and n are identical, which they don't have to be. Also keep in mind that the denominators have to be non-zero. So that's the reason why I said b and d cannot be equal to 0. Now keep in mind that I want to show something about the sum of m and n. So let's consider the sum, which by direct substitution would be a over b plus c over d. Now keep in mind that a, b, c, d are all integers, so the sums and products of integers will still be an integer. Furthermore, the denominator b and d were separately not equal to 0, so their product is also not going to be equal to 0. This is what we know as the zero product property. The zero product property basically says that for the product of two things to be 0, one of the two things must have been 0. In my case, b is not 0, d is not 0, so the product of them is not going to be 0 either. For it to be 0, one of the two numbers must have been 0. So what does this mean? This means so far that m plus n is a rational number because it's the ratio of integers divided by other integers, and the denominator integer is not equal to 0. That's exactly what we need to show, and so we are completely done.